Hello and welcome to another video. In this problem we're going to be going over bus routes, and in this one you're given an array routes representing bus routes where routes I is a bus route that the ith bus repeats forever. So essentially this is like a route and the bus just follows the route, it like loops through the route, right? So it'll go like 157, 157 and so on. It will keep doing it. And you will start at the bus stop source. You're not on any bus, and you want to go to bus stop target. You can travel between bus stops on buses only, and return the least number of buses you must take to travel from source to target. Return -1, if not possible. So this problem is kind of like, you kind of know what you want to do, right? Like it's kind of straightforward in what you want to do, where you want to figure out some kind of like breadth first search to get from the source to the target, right? Some kind of like graph traversal, shortest path, breadth first search, because every distance is one, right? From one bus to another bus. But it's kind of really hard to figure out like, how do I represent my graph and how do I actually do this? Because it's not a straightforward graph. Like you don't have straightforward edges. It's written in kind of a weird way. And so the real trick to this problem, and also the constraints are kind of tough. So the real trick is like, how do I actually build my graph? And then once I build my graph, like what's like an efficient traversal? And then you just need to do like a basic breadth first search of a graph once you figure it out. So let's go through the examples. In this first one, you start at 1 and you get to 6. So 1 is actually on bus 0. So you can take bus 0, and then you would take bus 0 to 7, and then you would get off at 7 here, and then you would go to 6 here. So you would take 2 buses. And in the second example, it's impossible to get to the end because if you look at source 15, so you can either get on this bus or this bus, but basically if you look, you have to get to this bus. So this bus has 9 and 13 edges and 12. So basically the only way to get to this node is from this bus here. So we can kind of work backwards a little bit. So you basically have to get to this node or this node, right? This node also has 12. So you have to get to this node or this node, but the problem is you can't get there because this bus only has stops at 7 and 12, and there are no 7s, and this bus only has stops at 9 and 13. So basically, if you start at 15, there's no way to get there, right? If you start 15 like on this bus, you can only go to 19. None of these have 19. If you start 15 on this bus, you can go to 4, 5, and 6. So, or actually, you can only go to 4 and 5. And 4 and 5 don't connect to anything else. So there basically aren't any connections. So I'm going to talk about 2 ways of doing this. One is a little bit more straightforward, and it's a bit slower. And then the other one is trickier, but it's faster. So we'll talk about the slower, a little bit more intuitive way first. And we're going to make 2 graphs here. So the first graph, we're going to have a key of node. Or sorry, not node. We'll call it not route either. What's a good name? Let's just say, yeah. Let's call it stop. Yeah, that's a good name. Let's call it stop. So we're going to have a key of stop, meaning like stop 1, stop 2, stop 7, and so on. And the value will be a set. So it's actually right over here. So the value will be a set of routes this stop connects. So for example, in this first example, like stop 1 is only on route 0, stop 2 is only on route 0, stop 7 connects route 0 and route 1. And these are like indexed, right? So this would be route 0, route 1, and so on, right? And then stop 3 is only on route 1, stop 6 is only on route 1, and stop 7 is, or I already have stop 7, but this is essentially what you would have, right? So step 1, you could do this, and this is pretty straightforward. You would just go through your routes, you'd keep track of the index, and then for every single number, you would just add whatever index you have to this thing here. So that part is pretty straightforward on how to do. So once we get that, then we have another step, and that is we are going to actually connect our routes. So to connect our routes, we're going to have all of our routes, and basically for our routes, ideally our key will be key will be route, and value will be set of routes we can get to. And we're going to use this stop thing to build that. So essentially what we're going to do here is for every single node, we're gonna have like a nested for loop for every single node. So for every single value, we will connect it to every other value. So in this case, there are only 2 values that we need to connect. But essentially, if we had something like, let's say node 7, and it would be like 1, 2, 3, or whatever, then basically we would connect these. So we'd say like, okay, let's connect 1 to 2 and 3. Let's connect 2 and 3, right? Let's connect all of these. So if we did have this in our nodes, then in our keys we'll have like 1 can go to 2 and 3, 2 can go to 1 and 3, 3 can go to 1 and 2. And so we're going to have this as well. And this is basically going to be a set, right? Because we don't want to have a bunch of duplicates. So essentially, we're going to have something like this where we have our stops and then we have our connected routes. So for this example, it's going to look like, let's see here. So in this case, only 0 and 1 are connected from this node 7. So it'll be like 1 will be connected to 0 and 0 will be connected to 1. And then once you have both of these, what you need to do is you need to have a queue that starts with all the routes that have the starting edge, right? So what that's going to look like in this example is all the routes that have the starting edge. So the starting edge is 1. So what are all the routes that have 1? Well, and we can also get that really quickly, right? We can get that really fast because we have this set of routes. So we're going to use both of these together. That's why I said it's going to be a little bit slow, but it's a little bit more intuitive. So we're going to have a set of routes, and basically all the routes with a starting edge is only going to be if it's edge, what was it, 0, I think, right? Or sorry, it's edge 1. So edge 1, only route 0 has that edge. So we're going to have route 0 here, and then we're just going to keep track of like a path length. So we'll make a path length 1 default, right? Because you have to take a bus. And you can check, there is like an edge case where if the source is the target, then you can just return 0 because you're basically there. So essentially you have this queue where you have, like I said, you're going to have an array of route and path length, or route, bus, whatever you want to call it. And then basically what you do is now that all of our routes are connected, now it's pretty straightforward, right? For every route, you just connect it to all other routes, and then you just check like, is my destination in my route? And that part is pretty straightforward. Now that you actually found a way to connect the routes, now it's pretty straightforward to figure out the rest of it, right? You just traverse from you have your queue with all of the routes that have the starting edge, and then from there you just traverse to all other routes and you have a visited set and all that kind of stuff. So that's like the easier way of doing it, and that will pass, but it's going to be a little bit slow if you just have both of these. Now we're going to talk about how to do this without this, and we will not be connecting the routes. We're only going to use this stop connection thing. And so let's actually go through the second example for that one because it's a little bit longer. So let's do that. So let's go through the second example with this, and we will, yeah. So let's get rid of this ideally. There we go. Okay. So let's build our stops for this last one. So we have, what are the stops we have? We can just build them up, right? So we have 4. And also let's actually draw the indices here. So this is route 0, route 1, route 2, route 3, route 4. Okay. So we have 4, and that's route 1. I don't think it's anywhere else. We have 5 on route 1. I don't think that's anywhere else. 6 on route 2. 7 on route 0. 9 on route 4. 12 on routes 0 and 4. 13 on route 4. Yeah, that's it. 15 on routes 1 and 3. And finally, 19 on route 3. Okay. So we have our source 15 and our target 12. So we're still going to have a queue, but instead of we're not going to connect our routes. Essentially what we're going to do is we're going to kind of have a visited set of our routes and our stops at the same time. So we'll have a visited set, visited routes, and we'll have a visited stops. And we'll still have this queue, but now it's going to be a little bit more efficient. And we also don't have like two graphs, right? So now the idea is we're still going to have this queue, and the queue will start at the initial route, right? So the queue will just start at the initial route with a path length of, or sorry, at the initial stop with a path length of 0, meaning like if we can just, if our source is our destination, we'll return 0. So our queue initially will start with 12 and, or sorry, 15 and 0, right? And it's going to be the stop and the path length, kind of like before. But now what we are going to do is we are going to pop. So and then we are gonna add this like visited routes. We are gonna add this route to the visited set as well, right? So it's gonna go to the visited stop here, 15, right when we put it into the queue. Okay. So now what we are going to do is we are going to actually like pop it, right? So we're going to pop this 15. We're going to check, is it our destination? Our target is 12, so no, it's not. So we're going to pop 15. Then we are going to check for every single bus for this route that we haven't visited yet. So route, bus, whatever you want to call it. So for 15, we haven't visited any buses yet at all. So we're going to check route 1 and route 3. So for route 1, there are nodes 4, 5, and 15. And essentially what we're going to do is we're going to add every single stop for this bus, for this route, bus, whatever, that we haven't visited yet into our queue. So we are going to add here. So we haven't visited 4, so we'll add 4, and we'll say that's one bus. Then we will add 5, and that's one bus, and 15 we did visit. Then we're going to see, is there any other bus for this route? There's also bus 3, so it has 15 and 19, so we will also add 19 and path length 1. Okay, now we get rid of this 15. Let's just do it like this. So we get rid of that, get rid of this. Now this is our queue. And so 15 is visited, and we're also going to mark the buses or the routes visited that we just went through, because we don't want to be like iterating through multiple buses to get routes, right? So we're going to mark we visited bus 1 and bus 3, I believe. Yeah, so we're going to mark 1 and 3 as visited. Okay, now we're going to pop this route. And so, oh, by the way, so also every single stop that we add to the queue, we're going to mark it as visited as well. Because as soon as it's in the queue, we don't need to add it in. We don't need to like do it again. Because a shortcut for a BFS where every path length is 1, as soon as your thing is in the queue, you can mark it to visited. It's not like a heap. If every path length is 1, if something is in a heap, if something is in a queue first, you don't need to add it again. Okay, so we visited 15, 4, 5, and 19. Okay, so we're gonna pop 4. We're gonna check, is it our target? No, it's not. And we're going to see what's in 4, what bus. So there's only bus 1, and we've already visited bus 1, so we don't really need to do anything there. So we're just going to pop, get rid of it. Now we're going to pop 5, and we're going to say, okay, so the only bus here is bus 1. We've already visited bus 1, so nothing to do here. And we're going to pop 19, and the only bus in 19 is bus 3. So nothing to do here as well. So we are basically, now we have an empty queue, so we return -1. So that's kind of like the idea behind this one, is you have a visited routes and a visited stops, and it's a lot more efficient because A, you don't have to have 2 graphs, and B, we're kind of like checking buses and stops at the same time. Definitely tricky, not easy to come up with. Like I said, the first one that I talked about is easier if you have the graph of routes and the graph of stops. That one's a lot more straightforward, and then you just use your routes and just find, like, use your routes to traverse. It's a lot more straightforward. But we're going to code this one up. Okay. So first of all, we're going to construct our graph with our like stops. So we'll call this stop to buses, and it's going to be default dict set. And basically what we need to do is, like I said, the key is going to be the stop, and then the buses or the routes will be the values. So we'll say for I route and enumerate routes, and for stop and route, we will say stop to buses, stop, add that route or that bus. So now we have our graph of the stops and all of the buses in there. Then we can also check, there is one more check, if our stop isn't, if our source or the target isn't in our stops, then we can just return false straight away. So we can say if source not in stop to buses or target not in stop to buses, then obviously we can never get there because it's not even in our graph. Right? Then we will just return -1. So now we're going to set up the BFS. So we are going to have the visited stops and the visited buses. So we'll say visited stops equals set and visited buses equals set. And what we're going to do is we are going to we're going to set up our initial queue, right? So we'll say if queue, so we'll say queue equals deck, and it's going to be initially, we will have, you can have an array of arrays or whatever you want to have. So I think what we want to have is we want to have the source, right? The source and then 0. And we also want to add this source to the visited set. So we'll just say to the visited stops. So we'll say visited stops dot add source. Okay. Now we pretty much do this BFS while our deck is not empty. So we are going to pop a stop and a bus changes or distance or whatever you want to call it bus changes equals q dot pop left. And basically our base case is if the stop is the target, right? So if stop is the target, then we will return the number of bus changes we had. And now this is where we're going to have our nested loop where we are going to go through every single bus for the stop, and then we're going to go in every single route for the bus as long as either one hasn't been visited. So we'll say for bus or route in stop to buses. Stop if bus not in visited buses. So if we already seen the bus, we don't need to traverse it again, right? That's like the thing that makes this one fast is we are marking them both as visited. So if the bus is not in the visited buses, we will add it in. And then we're going to say, basically, for this bus, we're going to try to go to all other stops. So for next stop in routes. So we're going to traverse this bus if we haven't before. Let's check all the stops. And if it hasn't been visited yet, so if next stop not in visited stops, then we will add it in there. Visited stops dot add next stop. And we will add it to the queue. So queue.append next stop and bus changes, right? Like distance or whatever you want to call it. The old bus changes, and every time we add a new stop, then we have one more bus essentially that we go on. And as always, if your queue is empty and you didn't find anything, just return -1 at the end. Now we pray that this is successful. Looks like it's not. Let's see. Oh. There we go. Okay. And so, yeah, so when I originally did this with both of the graphs, I think this was like 5,000 ms or something. So this is definitely like a significant speed up if you have both visited sets, but it's tricky to figure out. Honestly, I would say for this problem, especially in an interview setting, I would definitely go for the approach that I did in code, where you just have the two graphs that you make, right? The node that connects the stop graph, and then the nodes graph that actually connects routes. I think that one's like more intuitive. It's going to be slower, but like in a 45-minute interview, it's kind of hard to come up with like the optimal solution for hard problems. So, okay. So let's talk about the time and space. Pretty tricky for this one, I'd say. Might get it wrong. We'll see what happens. So let's go through all of this together, essentially. So in this section, to build up the graph, this is going to be like O of n, where n is the number of total routes you have, pretty much, right? So this is like, let's say k is like the average length of a route for a bus, and then let's say m is like the number of, yeah, let's say m is like the number of routes, and n is the number of stop to buses. This would be like k times m here. And then, yeah, and same thing for space for that one. So we can add that in right now, and we'll see if we have anything else. Okay, so this part is nothing. This part is also nothing. So now we have like our actual iteration. So essentially for this queue, we're going to traverse every single bus. And then, so we're going to traverse every single node, actually, and then every single bus on that node, right? Like when we do this, or like stop. So when we traverse every single node and every single bus on that node, that's going to be something like, I guess it would be like, if bus is m, it would be like this or something along those lines, where n is the stop and then m is like the number of buses, something like that. It's in reality it's going to be a lot smaller than this, but it's going to be something along these lines. Yeah, I think it like roughly. I think, like I said, it's kind of tricky. And then also for every bus, we have to traverse every single route for that bus, which is already this is already encountered into this part. So that part is basically nothing. So it's going to be something like this, where essentially for every single bus you have to traverse every single route for the bus, and then for every single for every single actual value in here, for every single stop, you have to traverse every single bus on that stop. So something like that. Now for the space, so I guess how big can the queue get as well? So for the queue, it can get length n, I guess, where n is like the number of stops. So that's something. Yeah, I think the queue can get length n, where n is the number of stops, because it's basically we're putting unique stops onto the queue. And then as far as the graph, I think it's like this already. So it's like something like this. Like I said, this problem is like, and with all these constraints that are kind of like ridiculous, like it's kind of hard to follow what's going on in all these constraints. It's not a straightforward time and space for sure. Yeah, I think I'll just leave it here. I don't want to talk about time and space for like 20 minutes, so I definitely could be wrong about this one. But yeah, hopefully you like this one. And if, like I said, if you can't come up with this one, or if, like, honestly, even once you've seen the solution, I would encourage you to maybe start with the easier one, where you have this graph and then the graph of routes, and you make the routes by using this. So essentially, like I showed it in the picture, for every single stop, you just do a nested loop through every single group of buses in the stop and connect them, and just have a set of connections for every bus, and like start there. And then for your starting queue, you would just start with every single bus that has the source in it. Because the buses are pretty cheap to traverse, there's only like 500. The real cost is the actual routes. But yeah, so hopefully you like this one. Definitely a tricky one, I would say. And if you did like it, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.